So let's go live again. Uh, uh, so now we have started three important properties of the Fourier transform. One is the delay, the other one is convolution, and third one is multiplication by an exponential. Then fourth, we are discussing that if a flip in time is a flip in frequency. Okay. And then there are others like multiplication in time is primarily convolution in frequency, a convolution in frequency. Into y exponential j, and it's actually a circular convolution, and we will learn about the circular convolution. So at this point, we don't worry ourselves with the circular convolution thingy. Okay, let's not worry about it. Let's just so then there is another one which says Parseval's theorem, but then there is a very interesting property and a set of properties which are called symmetric properties. Symmetric properties. And what the symmetric property says that if your signal is even, okay, even means that if you flip, you get the same thing. Flip, you get the same thing. If signal is even, your Fourier transform is also even. Your Fourier transform is also even. Okay. Example of an even signal is a cosine. We know cosine is an even signal. So if you flip it, it will remain cosine. Okay. And we know its Fourier transform is this. So if you flip the signal, you flip the Fourier transform, it remains the same. So flip even signal has an even Fourier transform, and similarly an odd signal has an odd Fourier transform. But the important is, what if signal is real? Real means it's a signal, and if you take its conjugate, it remains the same. And says if a signal is real, means you take its conjugate, there is no j, so it remains as is. Then the Fourier transform, though first of all, the Fourier transform of a real signal is not real. That's the problem. Is Hermitian symmetry. So this is called Hermitian symmetry. अच्छा, means के the Fourier transform, for example, आपका signal है A of n. Let's say A of n, U of n is a real signal. Okay, its Fourier transform is 1/1 minus A exponential minus j omega. Okay, so its Fourier transform has a Hermitian symmetry, means like if you replace exponential j omega with exponential minus j omega, then take its conjugate, it becomes the same. So let's first replace exponential j omega with exponential minus j omega. So it becomes 1 minus A exponential j omega. Now you take its conjugate, it becomes negative sign, so it becomes the same. So, okay, then why should I care? Why should I care about the Hermitian symmetry? The Hermitian symmetry is good. Why Hermitian symmetry is good? Because if you have a real signal, okay, and its Fourier transform is going to exhibit Hermitian symmetry. The transform is going to exhibit Hermitian symmetry. Then it means that its magnitude, important, very important property, its magnitude is going to be even, and its phase, the phase of the Fourier transform, is going to be odd. Okay, means any real signal, maybe it voice, maybe it video, ठीक है, कोई भी real signal है, voice is a real signal, data coming from sensor is a real signal. Once you plot its Fourier transform, the magnitude, because complex you have to plot the magnitude and phase. So whatever you see on this side, you are going to see the same, the magnitude of the Fourier transform. You're going to see the same thing on the other side. And remember, we are only concerned from spectrum from minus pi to pi. So it means that once, actually, I have to compute the Fourier transform using a computer program. The obvious question is, why should I compute this part? Once I have only computed this, and I know this part is going to be the same as this part, so I must not compute this. I should just replicate these values here. And more important is because I know that this is going to be the same as this, so I should only plot for real signals the magnitude of the Fourier transform going from 0 to pi. And remember, I told you earlier that pi is half of the sampling frequency. So this is an important property, that we should only calculate half of the Fourier transform as the magnitude is even symmetric and phase is odd symmetric. So this is a very important property of the Fourier transform, that real signals Fourier transform exhibit Hermitian symmetry, which is the magnitude and the phase are related. They are evenly symmetric or oddly symmetric. Okay. Then there is another, perhaps we have seen Fourier transform of many pairs, like we know Fourier transform of 1 is this, and then it is periodic over 2 pi, and we have spent a lot of time learning about that. And then we also know if it is an exponential j omega naught n, this Fourier transform is omega naught 2 pi. And we also know if it is cosine of omega naught n, then it's a doubly arrow, then its Fourier transform is. But can anybody tell what is the Fourier transform of delta of n? How many exponentials are there in delta of n? How many exponentials are there in delta of n? Anybody? Okay. So you may think that perhaps there is 0 exponential or 1 exponential, but generating an impulse, which is a signal and then it goes back, find out that there are not one, there are all exponentials, all possible perceivable exponential with same magnitude. So an impulse has all the frequencies in it. Okay, so delta of n has all the exponential in the entire spectrum of the same magnitude. So delta of n has all exponential. That's why delta of n Fourier transform is 1. Okay, so 1. So this is important. Delta of n Fourier transform is 1. So we need to remember this. So this is an important, and we can always, easily do this using the formula as well. Delta of n exponential minus j omega of n. N goes from minus infinity to infinity is. And we know delta of n, once it's multiplied with exponential minus j omega and you add all of them together, it is going to give you a 1. So from the formula we also know that it's not infinity, it's it depends how you take this, but it has a content of all the frequencies, equal contribution of all the frequencies. Okay. So this is has all the frequencies in it. Okay, now let's find the Fourier transform of something which is very important. Okay, inverse Fourier transform. Remember the property which says that convolution is multiplication in frequency. So this only tells us that first of all, you have a signal. No matter what type of signal you have, you plot it in frequency domain. Let's say it's a radio spectrum, so you have multiple channels. You plot that. Okay, and then H is like a scissor, which is going to cut the spectrum in the shape which you, or in a desired shape. For example, if you want only this part of the spectrum to remain in the signal and you want to filter the rest of them out, so you find out in design an H of n, use Fourier transform, or the frequency response is this. Yes, delta of n has equal contribution of all the frequencies in our digital spectrum. A question is, KG, if delta of n has equal contribution, yes, it has. In a delta of n, there is an equal contribution of all the frequencies. If you collect all the frequencies together of the same amplitude, in time domain, it gives you a delta of n. Okay, and same is the case. Perhaps it is easier to understand in analog domain. An analog impulse also, an analog impulse which is delta of t, and its Fourier transform is all frequencies from minus infinity to infinity. Okay, so because it's almost impossible to generate an impulse, a signal which has zero width and infinite height, so almost impossible to generate such a signal. Okay, such a signal which has width goes to 0 and 1 over delta goes to infinity, but area under the curve is 1. And you can see that, like, generating the signal means that you have to generate all the frequencies from minus infinity to infinity, which almost is impossible. So an impulse is impossible that you can generate an impulse. As a matter of fact, anything which is discontinuous is difficult to generate. Okay. So this is an important property, and so the inverse Fourier transform of something like this is also very important to learn, because this is our desired to cut a spectrum in a way that it should keep what we want to keep and it should filter out what we don't want to keep. So perhaps the most important expression is to find out the inverse Fourier transform. The expression for finding the inverse Fourier transform is this. So this is the most important expression. This, okay. Signal is not periodic. Signal is aperiodic. Okay, Fourier transform is periodic. So Fourier transform keeps repeating itself, but a digital spectrum can only have frequencies from -pi to pi. So this is the most important Fourier transform from systems perspective, that we want to cut the spectrum in a way that whatever we desire, these frequencies should remain unaltered. They go past through the filter or the system, and rest of the frequencies should go away. And that's why this course may also be titled as frequency selective filters. Okay, this may be another name of the course, frequency selective filters. Okay, so in order to find out that what is the impulse response, and remember the impulse response is the thing which you will convolve with the signal to get the desired output. So you take its inverse Fourier transform, and we remember the formula for the inverse Fourier transform is, it is this 1/2 pi minus pi 2 pi, okay, h exponential j omega exponential j omega and d omega. So now this is our h, so h is 1 primarily, but it is 1 from minus omega c to omega c. Its value is 1, and exponential j omega of n d omega. So this is what you get. So once you take its once you integrate it, so leave 1/2 pi here, so you got to have a jn, a jn and jn, right? A jn and jn, you need to have this. So, and then exponential gives you an exponential, so you have exponential j omega n, and your limits are omega c minus omega c, and you have j n. So this, once you put the limit, it is exponential j omega c n minus exponential minus j omega c n divided by 2j and pi n. This is, and this is the formula for sine, so it becomes sine omega c n over pi n. So this is very, very important expression. Very, very important expression. This is where the signal processing kind of starts from this expression. Let me give you its significance, why it is such an important expression, sine omega c n over pi n. Okay. All we are saying that if you have in frequency domain, you want something. This is also called an ideal. This is called an ideal system. This is an ideal system. Okay. It is h exponential j omega, and its inverse Fourier transform is sine omega c n over pi n. Let me plot sine omega c n over pi n as well. It is primarily a sine. It is a sink, that goes from minus infinity to infinity. It is a sinc function. Okay. This is the impulse response. So why should I worry about this? Because now you think about it, that you have voice, simple voice, and you want to filter, because remember the voice spectrum primarily goes from 0 to 21 kilohertz. And you want to only keep this voice from, because 0 to 4 kilohertz. For some reason, you want to filter the voice out. Okay, spectrum is, so you want to, why? Because you don't want to keep the high frequency contents for many applications like AM radio, even in FM, even in your telephony. You don't care about high frequency contents, because the high frequency contents makes the system expensive, and usually in high frequencies you have some very the music usually have frequency contents which are greater than some kilohertz. So this high quality music, for high quality music you need to have you need to keep these high frequencies. But if you only care about voice communication, even from 0 to 4 kilohertz, so all our exchanges only keep spectrum from 0 to 4 kilohertz. So you got to pass this voice, okay, through an h of n, which is this. So remember, if you want to filter out voice, you need to do the convolution. And now you think about this, a flip, once you flip it, it remains as is. Okay, and now you are dragging, and how many multiplications you have to do to find one output sample? Infinite many, because this has infinite samples. Number one. Number two, this is not causal system. Okay, this requires all the future samples, because h of minus 1 requires x of n plus 1. In the convolution summation, h of minus 2 requires x of n plus 2. So there are two issues with this. Number one, requires infinite many multiplication just to compute one output sample. And number two is requires all future samples to perform convolution. Okay. So obviously, neither we have, it's a live broadcast, you are talking to somebody on phone, and so you cannot just, collect all the samples till end of your conversation, and then you pass it through a filter, and then you pass it. It does not make any sense. So this is non-realizable. This is an ideal system. We want a system to be like this, but this is a non-realizable system. Okay? This is the main problem with an ideal system, that you cannot realize. It means you cannot write a computer program to implement this system. So you got to now compromise. Okay, if you want to implement a system, you got to compromise. A compromise means that has to be finite number of multiplication, and ideally I don't want to use any future sample. Okay, so you got to compromise here, you got to compromise here. Compromising this, okay, you don't want to do infinite many multiplications, so you say I'll cut it down. Whatever my budget is, let's say I can only perform, the application is such that I can only perform 200 multiplication for computing one output sample. Remember, convolution requires you, this is the convolution summation. So length of this is basically will tell you that how many multiplications and all the previous samples, because it's the minus. So what should your budget? It all depends upon your budget, that what is your budget. If you have designing an expensive system, so you may want to keep 200 of these samples, or 100 of these samples, or 50 of these samples. And this compromise, then you need to see that what is the effect of this compromise. Once you're compromising on the sync, an ideal sync, okay, so you again need to go back and take the Fourier transform. And once you take the Fourier transform, and remember the Caesar thing, that is basically you are cutting your spectrum. you will find out that that primarily is affecting your Fourier transform of the system like this. Okay. Why should I care? This is important for us to understand. Now the frequencies you want to keep, okay, 0 to 4 kilohertz. Some of the frequencies will be amplified and some will get attenuated a little. Maybe this is 1.1 and 0.99, but you are causing distortion in the desired frequency spectrum. Then you want to cut out all the frequencies from here onward, but you cannot do that in an ideal system. There will be some part of it that will get into your signal, the output signal, and then this is the undesired, the other channels. Okay, so you cannot get rid of them as well. A very little part of these the out of band signals would get into your signal, and depends how much you want to attenuate. Okay, here, and how fast you want to transit. So there again, engineering is all about trade-offs. A trade-off means that then you got to go back and spend more of these. Infinite multiplication means that this summation, as you know, goes from minus infinity to infinity. If your h of k goes from minus infinity to infinity, means that you have to run this summation. But if your h of k only goes from minus 10 to 10, okay, because then otherwise it is 0 and you don't multiply with 0, so you run this summation from minus 10 to 10. So you hate to primarily do infinite many multiplication, because you cannot do infinite many multiplication. So this is the summation which tells us that how many multiplication do we need to do. Okay, so you compromise on the, so this is your compromise. You say I don't care. Okay, so once you're compromising, this is what you're going to see, that if you keep m is equal to 5, means 5 sample on the left, 5 sample on the right, and 1 center in the middle. So this is your Fourier transform. Okay, and you don't like it because you see the transition is bad, out of band signals getting into this, and you don't like it. But if you say, okay, I'm willing to spend more, so 9 on left side, 9 on the other, and 1 of the sync, then you see you start getting better and better and better, getting closer and closer to the ideal response. Okay, so this summation, which otherwise was running from minus infinity to infinity, now runs from minus m to m, and this is the compromise. And by doing this, you are making it a finite impulse response system, because now the impulse response does not have infinite length. So this is the compromise, and we say we really don't care about the ideal response, or completely eradicating the voice, because sometimes our ear is not sensitive enough to hear very, very low amplitude voice that comes from the other channels. Okay, so usually we are happy, depending upon the application, of a little bit, very little of the sideband, which is 0.00001, getting into our signal, because that basically, this compromise reduces the cost of the system. So this system with 35 and 5 is 7 times more expensive. Okay, 7 times more expensive. So this is 3 times more expensive. Okay, it's almost twice that expensive. So engineering is all about a compromise which you need to make once you are designing a system. Obviously, you need to do better in getting closer to the ideal response, but engineering is all about finding the best trade-off. Okay, the best trade-off means that how much you are willing to spend. If it is an HD quality video or a CD quality music, and so then you may be more, you may want to spend more money. But if it is a cheap AM radio or FM radio, you may not want to, spend that much money, and you want to keep the system simple. So this is an important expression which we need to know. Okay. Now the last thing is about. So this I'll upload the lectures, and here you will find all the important properties. These are the properties. Remember the delay property, and this is flip in time property. Yes, you need to only have require current and previous input samples, and that's why you shift the impulse response from -m to m. Instead of it running from -m to m, it runs from 0 to 2m. So you shift and make it causal. So these properties are important, and these pairs are also important, and so you can always for your quizzes and sessions, especially we'll design quizzes, and those quizzes will be open book, open notes, and so you can just spend time and then upload. We'll give you 10 minutes, you do the quiz, and then you take a picture of the quiz and send us back. So once you take your quizzes, so now there is so we have actually covered one more thing which we still need to worry about is so the question about the causality. Let me answer the question about causality. Remember what is causality. Our y of n is n going from -infinity to infinity, h of k, x of n minus k. Let's say the only runs from -1 to infinity. Okay, from -1 to 0. For example, a very simple impulse response which has only two samples, -1 and 0. Okay, this is our h of n. So if I open this summation, so my y of n will be h of -1, x of n plus 1, plus h of 0, x of n. Okay, so this -1 or this -1 requires a future sample. So current index is n, so it requires a future sample. It's a non-causal system. If there are two of these samples, okay, if it starts -2, then you require h of -2, x of n plus 2. It requires another future sample. So as you are moving in the negative direction, your impulse response, you will be requiring those many future samples, which you don't like, because a future samples means a delay. You got to wait for the future samples to acquire, and then only you can do the processing. So in real-time signal processing, in 1D signal processing, you hate to use future samples in your computation. In image processing, you don't mind, because once you take an image, you have a complete image. So if you're processing this pixel, this is a future pixel, this is a previous pixel, so you have the complete image. So there you are not really worried about the future samples. But in 1D signal processing, so what we do is, once we are designing system, remember that system means that you have an infinite impulse, an infinite sync. This is your ideal system in time domain. And to make it realizable system, you cut it, chop it out, throw rest of the samples. You have -m and m. Okay, so these are the samples you are keeping. What is m depends how much you are willing to spend. Okay, now because this is non-causal, it requires m future samples, so you shift it in time. So this is how a system is going to look like. This is a realizable system. M depends upon the number of multiplications, at how good a response you want to have of your system. If you look at this in frequency domain, because remember, a shift in time would not cause any change in the frequency contents, because we know the property. So the magnitude of the Fourier transform is not going to change. The magnitude of the Fourier transform would be still something like this. Okay, it is only the phase, and usually we don't care. So you are going to disrupting phases. So you say, okay, I know that I'm basically here doing something with the phase, so I can live with that. So this is the ideal response, and that you shift, and the shift would cause so now we are also interested in finding out the Fourier transform of an IIR system that is represented with a difference equation. Okay, our difference equation is usually y of n plus a1 y of n minus 1 plus a n y of n minus n is equal to b naught x of n plus b1 x of n minus 1 x of n minus n. Okay, so I want to know what is h exponential j omega, whereas I know the property of the convolution which says y exponential j omega is actually multiplication. Convolution is multiplication in frequency domain. So h exponential j omega is actually y exponential j omega over x exponential j omega. Okay, and please remember, this is the frequency relationship, is in the frequency. You cannot say conversely that h of n is y of n over x of n. Absolutely not. Okay, because they are related with a convolution expression, not a multiplication expression. So this is not possible. They are related with a very complex relationship if you want to find out h of n, because you got to take h of n out of the summation. So it's not that trivial how to find out, but this is very trivial, right? Because of the multiplication relationship, not convolution relationship. So this is simple. So now we go and take Fourier transform of both sides. Okay, once you take Fourier transform of both sides, y of n is y of exponential j omega, and a delay in time is exponential minus j omega. You multiply the Fourier transform with exponential minus j omega. So this will look like this: y exponential j omega. This is going to this will be reduced into a very simple expression: minus j omega n y exponential j omega plus do a of n exponential minus j n omega. Sorry, there is no n in it. Y exponential j omega, and on the other side it is b naught x exponential j omega. Okay, for this, plus b1 exponential minus j omega x exponential j omega plus bm exponential minus j m omega x exponential j omega. Okay, so now you take this as common, and on right hand side take xx common, so you have, and then this. Okay, and in bracket you have 1 plus a1 exponential minus j omega plus an minus j omega n, and on right hand side you have exponential j omega b naught plus b1 exponential minus j omega bm exponential minus j omega m. Okay, so this is good. So now we know that we need to find out y. We need to find out y over x to get an h. So with this expression, you take this on the other side and this on this side. So you have y exponential j omega divided by x exponential j omega, which actually is h exponential j omega is equal to b naught plus b1 exponential minus j omega plus bm exponential minus j omega m divided by 1 plus a1 exponential minus j omega plus an exponential minus j omega n. ये बन गया expression. You don't have to go through all the maths. Looking here, you know that these are the coefficients of x and these are the coefficients of y. Given a difference equation, if I ask you find out h for this, so the answer is very simple, that the coefficients of x, this and this, will be in the numerator, and coefficients of y, this and this and this, will be in the denominator, and you can calculate it. By just looking at the equation, I can write the h exponential j omega is 5, which is this, plus 2 exponential minus j omega divided by 1, which is this, plus 0.9 exponential minus j omega plus 0.2 exponential minus 2 j omega. So this is the frequency response, which is very important. Remember that whenever you are designing a system, you must plot the magnitude of its frequency response to find out that how good a system you have designed, because that will give you the Caesar effect, that is it good. If it is good, because mostly you are designing frequency selective filter, so it will be something like this, right? I mean, as something like this. Ideally it should be like this, but you are never going to get an ideal whether you have an infinite impulse response system or you have a finite impulse response system. So this is an important, very important expression that we need to. So we are almost done. तो हम let me just end it. मुझे एक लतीफ़ा याद आ रहा है. So let me end it with a joke because of this lockdown situation. कि एक जो बच्चा है वो स्कूल से आता है, तो उसकी मदर उससे कहती हैं कि how was your day at school? तो बच्चा कहता है I have a terrible day in the office. माँ बड़ी परेशान होती है, वो कहती है बेटा but I sent you to school. But he said oh I means the principal's office. तो आजकल हमारे साथ यही हो रहा है. It's not that I'll be washing dishes, but you know we are working from home. So इंशाल्लाह अगली क्लास में जो हम इसी हफ्ते करेंगे 50 minutes की, we'll extend this and thank you very much. खुदा हाफिज़.